Hello, everyone. My name is Vitalii Emelianov, and today I'm excited to present our work on fairness in selection problems with strategic candidates. And this is a joint work with Nicolas, Gast, and Patrick Loiseau. So selection problems are problems in which, given multiple candidates, decision maker must select a small fraction of the best. And selection problems model many different decision-making scenarios with high social impact, such as hiring, college admission, or lending. In these scenarios, it is important to consider the fairness of the selection outcome. However, we observe that in many cases, people are discriminated by different demographic attributes like race, gender, or age. Recent literature on fairness and selection problems proposed different explanations for discrimination. For example, implicit bias literature assumes that there is one decision maker, and decision maker under-evaluates candidates of certain demographic groups. And this eventually leads to underrepresentation of this group. Another line of literature, which is the literature or on implicit or differential variance, assumes that the decision maker evaluates candidates without any bias, so his estimates of qualities are unbiased. However, the estimates are noisy, and the noise variance depends on the demographic group. And this, as a result, leads to underrepresentation of certain demographic groups. So in all this literature that I mentioned, it is assumed that the candidates' characteristics, for example, their qualities are fixed, and that they do not depend on the selection procedure. However, we know that there are many examples where where candidates, if they know that the selection rule, they try to adapt in order to increase the probability of a positive outcome. So in this work, we ask two questions. First, the question we ask is, what would be the impact of strategic behavior on resulting discrimination in selection problems? And the second question is really related to the first one. We know that usually if there is discrimination, decision maker try to use some affirmative action policies, and it is usually that usually are criticized. But in this work, we also ask what would be the effect of these fairness mechanisms in selections where the candidates are strategic. So we model the selection problem with strategic candidates as a population game. We assume that we have two demographic groups, H and L, and by PH and PL, I denote the proportions of candidates from each demographic group. I assume that there is a continuum of candidates, and each candidate chooses some effort MI according to some group-dependent distribution μg. So the effort can have an interpretation of the number of classes followed by a student, if we, for example, consider college admission problem, or it could be the number of different grades that the individual has, if we consider also college admission or hiring problem. We assume that the effort MI induces a random quality of the candidates, WI, and the quality of the candidates will be equal to the effort in expectation. We assume that decision maker is Bayesian, and he observes a noisy estimate of candidates' quality W hat. We took a motivation from this literature on differential variance, and we assume that the quality estimates are unbiased, but affected by noise, where the noise variance depends on the demographic group. So here, for example, we have H candidates, which are high noise candidates, and L candidates, which are low noise candidates. Decision maker receives these noisy estimates, and his objective is to select the best candidates, but he has some budget constraint, which we denote by alpha. So to better understand this model, let's consider an example. Here we assume that we have H candidates, and half of the population of H candidates makes an effort equal to 0, and half makes an effort equal to 15. This effort induces a distribution of quality, WH, And similarly, the L candidates make some effort. So half of the population makes effort equal to 5, and half makes an effort equal to 10. And this also induces some distribution of quality. Like I said, we assume that a decision maker observes noisy estimate of candidate's quality, where the noise variance depends on the demographic group. So here I show the distributions of noisy estimates W hat for H and L candidates. Because we assume that H candidates are high noise candidates and L candidates are low noise candidates, the distribution of estimated quality for H candidates has longer tails compared to the distribution for L candidates. Decision maker is assumed Bayesian, so he can estimate the expected posterior quality given the noisy estimate. So on the figure below, I show the distribution of the posterior expected quality for two demographic groups. And because the noise of the estimation for H candidates is greater, then the posterior distribution will be more shrank towards the mean for these candidates compared to L candidates. Decision maker wants to select the best, so he sorts the candidate with respect to the expected posterior quality and selects the best alpha, the proportion alpha. And he does so by applying a selection threshold theta. When he does so, he selects at some probability with from the L candidates and with some probability from H group. And by RL and RH, I denote the corresponding selection rates. So in this example, we see that L candidates are underrepresented because the area under the curve is smaller for them compared to the area under the curve for the H candidates. We assume that candidates attains a utility, which is a function of the effort that he makes and the selection threshold. He receives a reward of size S if he is selected. So the reward can have an interpretation of a salary if we think about, for example, a hiring problem. And he receives a reward of size 0 if he is not accepted. In both cases, he pays the quadratic cost of effort. So it is a function of the effort and also a function of the cost coefficient. So the cost coefficient depends on the demographic group in our model, which has an interpretation of different circumstances that candidates have. So in college admission or hiring, it could be the income of candidate's parents, or it could be, for example, the country of the origin. So the cost of effort affects how much effort the candidates can make, and it really depends on the circumstances of the candidates. We assume that candidates aim at maximizing the expected utility given the selection threshold, and this induces a game among the candidates. So they compete in order to receive this reward of size S. We study Nash equilibrium of this game, and we use the standard definition of Nash equilibrium for population games, where at equilibrium, no candidate has incentive in changing his effort. In the rest of the paper, in the rest of the talk, we will study the Nash equilibrium of this game, which exists and which is unique, as we prove in our theorem. So I would like to start with our first result, which is the characterization of the best response of a candidate. We show that when the reward is large, the best response of a candidate grows linearly with the threshold, as I show on this figure. And then when it reaches a certain threshold, which we call the dropout threshold, the effort drops down and it is decreasing. The dropout threshold depends on the demographic group. So here we see that H candidates drop out later than L candidates. And we will see later in this talk that the group that has larger dropout threshold would be mostly represented at equilibrium. We characterize the behavior of the dropout threshold. We show that when the reward is large, if the cost coefficient is group independent, CH is equal to CL, then the group which has higher noise of variance will have a higher dropout threshold. When the cost coefficient depends on the demographic group, then the group which is cost advantaged will have a higher dropout threshold. And it is important to mention that in this case, the behavior does not really depend on the variance. So when the cost is group dependent, the variance has a second order effect on the dropout. This characterization of the best response allows us to fully characterize the equilibrium of the game. Here I use some notation. I denote by mu bar G the average effort induced by a group made by group G at equilibrium. And similarly by R bar G, I denote the average selection rate for group G at equilibrium. Our main result is that for any selection rate alpha and and for large enough reward S at equilibrium, if the cost coefficient does not depend on the demographic group, then the high noise candidates will make a greater effort and they will be overrepresented. And this result is in contrast with the result for the non-strategic setting obtained in the previous literature. So to prove this result, we studied the limit of the equilibrium efforts and equilibrium selection rates. So this expression is a bit complicated. So I will depict it on this graph. So I plot this ratio as a function of alpha. In this case, the proportion of H and L candidates is the same. And we see that when the selection size is smaller than the size of the high noise candidates, the low noise candidates will not be at all selected. So in this region, we will not see at all the low noise candidate in the selection. However, when the selection size is larger than the size of the high noise candidates, we must select at least a little bit from the low noise candidate group, and the ratio increases. But overall, we see that it is always smaller than 1. We observe the similar behavior for a finite values of S. We see that the curves are quite close to the case of infinite S. For the case of group-dependent costs, we show that cost advantage candidates make greater effort and they will be overrepresented. And again, we see that here the noise does not play any role. It has a second order impact on discrimination where the cost of effort depends on the demographic group. So overall, we show that for both cases of group-dependent noise or group-dependent cost of effort, one of the demographic group is always underrepresented at equilibrium. We know that in these cases, when one of the group is underrepresented, for example, decision makers can use different fairness mechanisms. For example, they can provide some quotas to some candidates, or they might ensure that selection rates should be close in order to guarantee equality of representation. The strongest condition among them is what is called demographic parity mechanism. And the demographic parity mechanism requires that selection probability for each group should be equal. And because this is a selection problem, they should be equal to the selection size alpha. Demographic parity mechanism is always criticized because it may seem that they discourage candidates to make effort. In this part of the talk, we ask what would be the impact of the demographic parity mechanism on selection where candidates are strategic. So demographic parity mechanism reduces the competition among the candidates because they must be selected at equal rates, and the competition will be only among the candidates from the same group. And so we ask what is the impact, and we show our first result is that demographic parity always encourages the candidates from the previously underrepresented group to make a larger effort. So to do that, we consider this limit of equilibrium efforts for the demographic parity constrained decision maker and for the unconstrained decision maker that we studied previously in this talk. And we see that this limit is always greater than 1. Demographic parity can discourage previously overrepresented groups to make a larger effort, but we show that under some conditions it can also encourage these candidates to make a greater effort. We also study how the demographic parity affects the selection utility of a decision maker who maximizes the expected utility of selected cohort of candidates. We show that surprisingly, demographic parity mechanism can increase the selection utility of a decision maker. To do that, we consider the utilities of the unconstrained decision maker that we studied before and the demographic parity constrained decision maker, which must select with equal proportions from each group. And we show that this limit has the following form. Again, this expression might seem a bit complicated, but I show it on this graph as a function of alpha. So we see that in this example where the high noise candidates and low noise candidates have equal representation in the population, we see that for selection sizes which are small, demographic parity only decreases the selection utility. However, for this region where selection size is greater than the size of the cost-advantaged group, demographic parity actually increases the selection utility because this quantity is smaller than 1. So we can understand this as follows. So if the selection size is too big, then cost advantage candidates will not have an incentive to compete because they will compete only with candidates who are cost disadvantaged. However, when the selection size, however, when we impose demographic parity, they will need to compete with each other with candidates from the same group, and they need to increase their effort. And as a result, it increases the utility of selection when we impose demographic parity. So overall, we show that demographic parity can actually increase the selection utility when candidates are strategic, even for a Bayesian decision maker. So I can conclude here. So in this work, we proposed a model of selection with strategic candidates. We show that both group-dependent cost of effort and group-dependent noise leads to underrepresentation of some demographic groups. And we show that the resulting discrimination is open for an opposite group compared to the one observed in the non-strategic setting. We also studied how demographic parity affects the incentives of candidates and the utility of selection for a decision maker. We show that demographic parity actually encourages the previously underrepresented group to make a greater effort. And we also show that demographic parity can increase the selection utility even for a Bayesian decision maker. So Bayesian non-strategic decision maker is not optimal when candidates are strategic. Additionally, we study in this paper a convergence of different dynamics to Nash equilibrium. We do numerical experiments, and we show that the best response dynamics converges, but to something which is quite different from the Nash equilibrium. However, we observe in our experiments that the fictitious play dynamics does converge to the Nash equilibrium. We can consider different future perspectives on this work. First, we studied the case only of two groups. However, we think that we can easily extend this to the case of more than two groups. We consider only quadratic cost function for a candidate, but we could have considered the monomial cost function, and the degree of the monomial will be another important parameter in this game, together with the cost of effort and the variance. And we could have considered different decision makers or candidates' utility. For example, in this work, we considered risk-averse decision maker, but if we were to, risk-neutral decision maker, but if we were to consider risk-averse decision maker, then we would have an additional bias term, which will depend on the noise variance, and it would be interesting to consider this setting and as well in this work. Thank you for your attention. I will be happy to answer your questions.
Great. I realize over time, so if you want to jump, you can. But if there's questions in the room, got one? Can you shout at that mic for me? Mic here in the middle of the second room. Just shout at it.
In the slide number 5, when we have group-dependent cost coefficients, is the assumption that the reward is large highly plays a role in the cutoff that you said the cutoff for the lower cost, the more advantaged group is higher?
Sorry, I cannot hear you well for some reason. There is some echo, so maybe you can repeat the question. Or
in the slide number 5,
yeah,
and in the group-dependent cost coefficient, when you wanted to say the drop-off of one group is corresponding to their, the relative ratio of their cost. And does the assumption that the reward is so large plays a big role here?
yeah. Actually, here I presented only the case of very large reward, but we have also the case of small rewards in the paper. And here we can have an explicit expression. And here the situation is a bit more complicated. So indeed, I cannot really say. So I can say that the case of large reward is important, but we have also some results for the case of small rewards S. And here the situation is not that kind of clear as the case for the large rewards.
Yeah, because I guess you need that large reward to cancel the effect of difference in variances, yeah? You mean
yeah,
no
in a way,
matter
yeah.
how different are the variants, you're gonna get the same threshold relativeness between two groups.
Yeah, yeah. Indeed, for large S, it somehow cancels the effect of the variance.
Great. We'll wrap it up there. Thank you, everyone, for your time.
Thank you.